Hi, student and audience. It's time for the second lecture of this lecture series. The content of this lecture is a converter frequency response. In the previous lecture, we discussed all the details about the frequency response of 3 basic converters. And in this lecture, we'll apply those basics and fundamentals to the buck converter to investigate the frequency response of 3 different transfer functions: input-output transfer function, and the duty ratio to output transfer function, and the load current to output transfer function. In addition, we will discuss the implication of frequency response adapted to the PWM converters in comparison with those of linear time invariant systems, and we discuss the difference and the similarity between them to emphasize the unique characteristic of frequency response of the PWM converters. Now we start the discussions about schematic and small signal model of buck converter. So this is buck converter, okay? And we are assuming the continuous conduction mode. Assume this is just normal operational mode. So DCM will be handled separately. And this is buck converter. And its small signal model is this one. And usually this part is called SPDT switch, means single pole double through switch. Function of this pair of this active and passive switch is functionally same as this. This one. This is the A, P, C, and this is pole. Okay? This pole is always connected either of A or P. So there is a single pole. This is called through. So one pole, two through, single pole, double through switch. Or they call it PWM switch. Okay? Because this operation of switch is based on the PWM, pulse width modulation scheme. So they call it PWM switch. And the small signal model of this is everything remains the same. Just replace this one with this one. We introduced this in the previous lecture slide. Okay? And this is called PWM switch model. PWM switch model. Okay? There is one PWM switch model because the guy who derived this, who studied this, named it as PWM switch. Okay? So this is kind of a proper noun. So PWM switch model. But the detailed function indicate this is the small signal model of PWM switch. Okay? So this small signal model of PWM switch is called PWM switch model in short. Okay? Due to the guy who derived this in his paper. His name is Bode. Okay? One famous guy in power electronics. Okay? So this is the small signal model. All right. Then you are interested in transfer function of this converter with parasitic resistance. Parasitic resistance means this inductor is containing this series resistance, which is ESR, and the capacitor is also containing this parasitic resistance. Capacitor is looks like this. This is capacitor. So capacitor, structure of capacitor is very simple theoretically. It has 2 parallel plates and it is filled with some dielectric material. So everything is ideal. Then this has only capacitance, but this material is not ideal. This dielectric material has something less than ideal. But there is some resistive component is coming in. The resistor inside of this material is taken out of here. Okay? And it is represented like this. This is called the series resistance, equivalent series resistance of capacitor, ESR. So there are 2 ESRs, one from this inductor, the other from this capacitor. Okay? They call it parasitic resistance. You should consider this one. So they can be very small, but they have profound impact. significant impact on small signal dynamics, power stage dynamics, though they should be considered. Okay? So this is the model, complete model. All right? So you are interested in transfer function from here to there. Okay? When evaluating transfer function from here, there, this is considered dead. Inactive means open. It's not present here. Okay? And another one is this is dead means this is the open, it's not present here. And this is 0 means this voltage source is shorted. Okay? That means this Vs is directly applied here. This hat means small signal sinusoidal component. Sinusoidal component with small magnitude. We call it hat. Hat is this one. Hat. Okay? In Korean, sakat. Okay? Small sakat. Hat. Okay? So this is open. This showed it. And it is ideal transformer. Then it is multiplied by this. So it appears here. And this one, you have R, C, L, C, R. This one is what? Second stage, second order low pass filter. You know this, okay? Forget about this small resistance. Then you have a combination of the L, C, R is what? Low pass filter. You learn this a lot, many times, okay? So there is a low pass filter embedded in small signal model. So this is this comes to denominator. This is the second order equation because we have two reactive components. And here, see here, but there is a second order, okay? This form is called frequency response form. So you can use another form. S square comes first and something. But we prefer this one, okay? And numerator is D is coming, okay? D is coming here in front. And there is one term. This is called 0. It's called omega ESR. So this 0 is coming from the ESR of this capacitor, and we call it ESR 0. Okay? You can easily derive this, right? So this, by simply calculating this is very easy. So D is coming here. That's the low frequency gain, because at low frequencies, at DC, S is 0, 0, 0. They are gone, okay? They becomes 1. All of them becomes 1. Then you have D. So this is the DC gain is coming first. Then you have D times Vs is coming here. And this one is what? Just voltage division, okay? You can easily evaluate this and put in this form. And this omega ESR and this omega naught, okay? It's called the naught. Naught means void, empty, 0, something like that, naught, okay? So omega naught is given by this exact expression, but this RL and RC, they are parasitic component, very small, so ignore this, and cancel this, then this one, okay? This is approximation, but very good approximation. Because this one is really small, maybe 100 times smaller than this. So this is a good approximation. And this Q is given by this, okay? And this omega naught is here. So this looks complicated, okay? But ignore this. R is very small, and this one is small. Ignore all of them. Then R is coming here, and this is gone. And C is here. No, C is gone. This term is gone. L is here. But this one is coming on the top. Then equation becomes this. Okay? Or you can derive this, right? And factorize this. This is called what? This is called the quality factor. Okay? This is called the quality factor. Quality factor is, by definition, representing the quality of something. Okay? Quality of what? Quality of this circuit as energy storage component. Okay? So this original definition is related with the energy storage type resonance circuit analysis, but we are using same terminology here, so it's called the quality factor. Okay, and there is another expression in control people. They want to use this zeta. It's called the damping ratio, and the relationship between them is, it has this kind of relationship. Okay, so this one, so we call it quality factor. Okay, it's good. It's important to remember this quality factor represent the quality of this circuit as energy storage component. Okay, energy dissipation occurs here. Assume this is 0, this is 0. So you have L and C. This R is infinity. Then this is the open. Then you have L and C. Energy won't be dissipated. That means quality factor is very good. Quality factor is infinity. Okay. So if R increase, then quality factor is increasing. Okay, so this expression makes sense, right? If R is very large, then power dissipation here is very small because current will be small, Q will be large. Okay, so this is okay. This expression is good, is correct, makes sense, right? And you have this one, C and L. Okay, L dimension of the L is impedance. Dimension of C is what? This is admittance. Okay, so admittance is coming here. Then it looks like impedance in the denominator. So we have impedance squared, and we have square root. That becomes the same, similar to R. So we have R divided by R. That becomes what? Some number. Okay, this should be dimensionless number. To make this one dimensionless number, C should come in upstairs, L should come in the downstairs. Okay, and R comes here because if R is increased, Q becomes quality factor, becomes good, becomes larger. Understand this? Okay. If you change the structure of this, the expression will be changed. You shouldn't remember this. It depends on the variation of this circuit with different orientation, arrangement, it will be different. Okay? So don't try to remember this. Try to remember this definition of this. Okay? This should be the dimensionless number. Alright? So with this is the assumption, very good assumption. Usually this is satisfied. This is some number. 5 ohm, this is 0.01, something like that. 10 milliohm, something like that. Okay? This is the more than sufficient to use this. Okay? And 0 is coming here. 0 is coming here. Right? And this is the transfer function from duty ratio to output. For that case, this is 0. I'm talking about the superposition principle. This is 0, showed it. You have two dependent sources, voltage source and current source, but you don't have to worry about this. Because this is showed it, then this current will circulate through this. It won't go the other side of transformer, okay? Because it has showed it pass, so it circulates forever, all right? Then this is grounded, then this is multiply this, and remaining term is this. So Vs is coming here, and then that voltage is transformed to voltage division, so you have the same expression here. Okay? Only difference is coming here. Okay? You don't have to derive this. It's just shown here. By seeing this, you directly write down here. Write down like this. Okay? In this course, we try to minimize the unnecessary calculation. Okay? Use your insight. Use your circuit property, and use your educated guess or educated approximation. Okay? So deriving this is very stupid. Take time. You will make, I'm sure you will make error. Okay? Forget about that. Just it is written in the textbook, right? And last one is this is input and this is output, okay? And this is shaded, and this is shaded. This is 0. Then this is shaded, right? In ideal transformer, primary transformer winding is shaded. Then secondary winding is shaded. Okay? That's the relationship. Circuit relationship of ideal transformer that comes from the definition of ideal transformer. So this is shaded. This is shaded. Okay? Then we have this. Everything is shaded. Then we have this in parallel with this. Okay? So this GP is load current to output transfer function is simply parallel combination of these three branches. Okay? One of branch impedance becomes 0, then this impedance becomes 0 because they are parallel combination. At one frequency, at this frequency, this becomes 0. Then this becomes 0. Okay? At this frequency, this becomes 0. Okay? Then it becomes 0. Okay? So this numerator are the same. Okay? That's a characteristic of linear time invariant system. All the transfer functions have the same denominator. So denominator remain the same, but it has 0, 0. One 0 is coming here, another 0 is coming here. There are two zeros. How about this? You have 0 here by equation, but that can be easily seen. This RC, the impedance of this branch is RC plus this one, okay? Then at this frequency, if S is 1 divided by CRC, negative sign in front, then this impedance becomes 0, okay? So this impedance is 0, then whatever appears here, output should be 0. Why? This is 0, shaded, okay? So this is shaded. So then the voltage is 0, output is 0. So that is 0, okay? So with this structure, there should be always 0. That 0 is called the ESR 0, okay? 1 over CRC. Since impedance of this is 0, if impedance is 0, then voltage should be 0, okay? The voltage source is sometimes it comes here, it really doesn't matter. So it has same 0 here, okay? And this one has 0, and that 0 is because of this, and another 0 is you have this one, SL plus RL is 0 when S is negative, RL divided by L is true. Okay? So if you have this structure, there should be ESR 0, and another 0 is appearing only in the output impedance. Not this one. Okay? Okay? All right, then let me finish up this page. I'm behind the schedule. Okay. All right. Asymptotic plot. Let me take a look at this. This DC is D. Okay. So low frequency gain start from 20 log D, and it hit this one, this double pole at omega naught. Okay. Usually the relationship between this is this one, omega G is coming first at very low frequency, omega naught is double pole frequency is coming in the middle, and omega ESR is coming last. Okay, so here DC gain, low frequency gain is 20 log Vs, and it hit mid. They are same thing. This one, double 0. So this slope is changing from 0 slope to -2 slope. Okay. Minus 2 slope means what? Minus 40 dB per decade. Minus 1 slope means minus 20 dB per decade. Okay. That is a term I'm using. That is a term used in all the previous lectures, my lectures, in undergrad course and graduate course. So I'm using this. Minus 2 becomes minus 1 because there is a 0. Okay. The pole is descending. This slope, double pole twice, single pole once, minus 20 dB per decade, minus 1 dB decade, and the single 0 is raising the slope by 1, okay, plus 1. So at this 0, minus 2 slope becomes minus 1 slope. And this one is 20 log Vs, and there is a peaking. You know this, okay? This is the accurate expression, and size of peaking in log scale is 20 log Q, and Q is called the damping factor, damping ratio, or quality factor, I'm sorry. Damping factor is something else. Quality factor. Q comes from the quality. Okay, expression of this, again, when R becomes infinity, this becomes infinity because there is no power loss, and the quality becomes infinity. Okay, this means no power loss or no damping. Damping means, damping, okay? Damping associated with power loss. Power is consumed. The energy is dissipated in the register, that means damped. Okay, this is called, when this in door, there's something here, this is called damper. All right, so because of this, I can close this door slowly, otherwise you will move forward, back and forth forever. Okay, so that is called the damper. So I'm not talking about damping, so something other than that, something else. So quality factor is very bad here. Right? Okay, quality factor is infinity. It won't stop. Okay. All right. So GVD, we have this, and this GVS this is coming below this. Why? This one is less than 1. Okay. D is ratio of duty cycle to on time period. Maximum value is 1, minimum value 0. Okay. So it is smaller than 0 dB. And we have the corner frequencies. This is not resonant frequency. Don't call it resonant frequency. Resonant frequency is something else. This is simply double pole frequency. Omega ESR, omega G. So this is the second order low pass filter characteristic is apparent in transfer function or in circuit structure. Okay? Or in the operational principle of the converter, or any other PWM converter, there should be the low pass, the second order low pass filter in this power stage transfer function. Okay? And this one is transfer function of this. Okay? So it has this double pole, this is 0, and the low frequency gain, this is important. Low frequency gain is at low frequency is opened, this RA, showed it RA. So RA is coming here at very high frequency. At very high frequency, this one, think about this one. This is the open circuit, right? Because of L here, and this is just showed it because of the C. Then you have parallel combination of the R and RC, but this guy is much, much smaller than this. Then approximately high frequency gain of this GP, high frequency value of GP is RC. Okay, so it starts from this RL and with at RC in between there is a 0 at low frequencies. So 0 is here. So 0 is coming. Okay, let me sketch this 0. Low frequency RL 0 plus 1 and double pole is here. Okay, then this plus 1 is reduced by twice, becomes minus 1, and this omega ESI is coming here, and it becomes flat, like this. That is shown here. Okay? So second order low pass filter character is apparent from in the transfer functions and the structure of small signal model or operation of three-phase converters. Okay? Okay? This is previous lecture slide, and I think I made one mistake in the last lecture slide. This one. This is about the transfer functions of a converter. So we went through the GBS derivation, GVD, and we talked about the GPS. When evaluating the GPS, you are looking this circuit from this point, and this one is 0, this one is 0, 0, everything is 0. That means the primary winding of this ideal transformer is shorted. In ideal transformer, if one winding is shorted, the remaining windings, all of them are shorted too, based on the circuit equation of ideal transformer. So this is shorted. Then what we are looking at is actually this parallel combination of this branch and this branch and this branch. And then if you use your circuit analysis technique, you can derive this. Okay? But it's better to use your insight to understand the high frequency and low frequency behavior of this load current to output transfer function. Okay, so at very high frequencies, when with, oh, I'm sorry, I intended to use this one, with at DC omega is 0, then this is opened and this is shorted. Okay, this is shorted, this is opened. Then what you have is parallel combination of RL and RC. Not RC. RL and R. Okay, so at low frequency or DC, GP is simply parallel combination of RL and R. RL is very small compared with load distance R. So it is approximated to RL here. Okay? So RL here. If you put 0 here, then you will get RL. Okay? But from this simple circuit analysis, you can easily confirm that is true. And when omega becomes infinity, then this is open, this is shorted, then what we have is a parallel combination of RC and R. So at very high frequencies, GP is simply RC parallel R. Then this becomes RC approximately. Okay, I'm sorry, it's too crowded. All right, so this is the better way of understanding this. And last time, based on this analysis, we sketched this. This is the asymptotic plot or Bode plot of three transfer functions. This is the duty ratio to output transfer function. This is the input voltage to output transfer function. This is the load current to output transfer function. So, as I said previously, so it has these characteristics. So the low frequency asymptote is here, and omega naught is the double pole. The slope is changed from 0 to -2. -2 means minus 40 dB per decade, and there is a ESR 0. This is a 0. So this slope will be increased by 1. So final slope is minus 20 dB per decade. Okay. So then this is the duty ratio to output transfer function, and this is the input to output transfer function at DC voltage gain of buck converter is D. Right? So buck converter output is given by D times input. So this low frequency value is 20 log D, and you have the same thing. And this is the second order characteristic. This is the second order low pass filter because we have L and C. So order is 2, and because of this, we have some peaking here, and the magnitude of this peaking is given by 20 log Q. Okay, so maybe you know this from the circuit analysis or electronics or control courses. And this is the output, the node current to output transfer function, and low frequency asymptotic is this. Actually, this is RL, parallel R, which is very similar to the RL, and the high frequency asymptotic is RC. Actually, this is the R, parallel with RC, can be approximated to RC, okay? And we have this low frequency 0, omega G, and this double pole, and we have ESR 0. This is usually the case, this omega G occurs at very low frequency, and this double pole frequency is coming in the middle. And this is omega ESR is usually coming at higher frequency. Okay. So I'd like to substantiate the proof. I want to prove this theoretical prediction using this PSIM simulation. So this is the PSIM file I explained earlier. So there are two PSIM files in one sheet or one screen. So this part is switch model or converter simulation, okay? And this is the small signal model. So this is the small signal model is converted to the PSIM code, and the switch model is converted to the PSIM program. So PSIM program is actually the circuit schematic of the converter. So this is a closed loop controlled converter. No, not closed loop, because this is the open, this is output, and this will generate the duty ratio modulation. So there is no connection in between. This is the open loop. Okay. With this, you can simulate the input to output transfer function using this time domain circuit model. Let me explain some details about this. So this method is called computational method. We use the actual time domain simulation. This switch actually is switching, is turned on, turned off, turned off, turned on, something like that. Okay, and this is the constant voltage, and this is the lamp function, and the height of lamp is this one. Height of lamp is 3.8. So this is the lamp function, and this is the fixed control voltage. This is the unit gain buffer. So voltage gain from here to there is just 1. So this maximum is VM. We use the notation VM 3.8, and this value is 0.95. Okay. Then duty ratio is simply ratio of this 0.95 divided by 3.8 is 1/4. So this is the steady state duty ratio. Okay. If you simulate this, you will see this output is just 4 volts, because duty ratio is 1/4. So 1/4 times 16 is 4. Okay. Then you are just watching the steady state value of our voltage. Now you add something in this voltage. Previously, this was a constant value. Now you are adding some sinusoidal variation here. Sinusoidal variation here. Okay. Then our voltage previously it was 4 volt, as I explained earlier. So this is a 4 volt. This is 4. Okay. But because of this sinusoidal component, there is a sinusoidal disturbance here. So our voltage will be changed like this. Okay. So then with this, you can plot this. This is the plot of frequency response. The frequency response is the response of our voltage due to the sinusoidal variation in the input voltage. Okay. So this magnitude of this can be input, and the magnitude of this is output. And from this simulator, it's just taking out extracting this sinusoidal component of our voltage, and it compares the result with this and evaluate the ratio between the magnitude of this one and this one, and put one dot here. That is called sinusoidal response at particular frequency. So now this simulator changes the frequency of this perturbation. So from this frequency, this is the 100 hertz, and this is the 10 kilohertz, and this simulator sweep this, okay? So it generates one point with this and increase this frequency and generate another data, one here, and another pair here, and that this will trace out some curve. This is the frequency response curve. This is the same as the definition of frequency response of something, but this is the nonlinear circuit. But still, we can use the concept of frequency response in this manner using this program. So we perform the time domain simulation, and from those results, we obtain the frequency response of this. Okay, so this is one story. You can do this without any prior knowledge about the small signal modeling or anything. Okay, so you can blindly use this program to generate this. This is the magnitude curve, and this is the phase curve. This is one way. This is maybe the brute force way. You don't need any knowledge about the modeling and the small signal model of something, but this is the small signal model. So this is the small signal model, okay, of this buck converter power stage, where this PWM switch is replaced with PWM switch model. So from this, you can analyze this circuit, and for example, the control to output transfer function, input to output transfer function, GBS is given by D. This is GBS, right? This is the D, okay? So low frequency value is D, right? When we evaluate the input to output transfer function, this D is 0, D hat is 0, this is shorted, this is open, and this VS is directly applied here and multiplied by this turns ratio D and divided by 2 impedances, okay? That result is this one, S divided by omega ESR, and 1 plus Q divided by, S divided by Q omega 0, omega naught. Oh boy. Plus S squared omega naught squared. Okay? So this is the result of the circuit analysis of this small signal circuit model. And previously, the Bode plot of this is this one, this curve. Okay? So this is very similar to this, one of this. Okay? Actually, there are two curves. One is this blue curve is generated from this simulation of this circuit. This is the small signal circuit, linear invariant circuit, and this is the PSIM model of this. So this is converted to this, okay? And this is the ideal transformer, and the 0.25 is duty ratio, steady state duty ratio, and this is the used to model this dependent voltage source and dependent current source, and the coefficient of this is IL, which is DC, value of inductor current. Because our voltage 4 volt, we have 1 ohm resistor. So average value of this is same as this one. So inductor current is 4 amp. So we have 4 here, something like this. Okay. So this is the circuit model of this, and you perform small signal simulation. some AC analysis, and you generate this curve, this green curve, this blue curve, okay? And the black one, this thin curve is a result of this. They're the same up to this frequency. That means this small signal model is correct, right? And it generates the same result as this computational method. So we confirm the validity of this approach. But in here, it has some noise. This noise is coming from the simulator because at high frequencies, the signal level is very small. Then some round of noise in the computer will generate this spike noise. This garbage, you just ignore this. Okay? And we evaluate this. So D is 0.25 and 20 log D is this one, minus 12 dB, and frequency of double pole omega naught is this one. So we have 2 pi, so this is the hertz. So this is 1.2 kilohertz, and the value of the Q is this one, okay? We went through this, okay? And that value is this, 20 log 3.4 is this, and omega ESR is given by this, which is this, okay? And I compared the simulation result of this one, which are the same, except this high frequency noise, and this is the double pole frequency, and this is the ESR 0, and this is the peaking due to the Q, right? And at this frequency, phase is 0 because this is the constant, okay? And at this frequency, phase is declined. At this frequency, phase becomes minus 90 degree, and it will go down further, but there is a 0, phase is boost, so final phase is minus 90 degree, okay? So this confirms the small signal model is accurate, okay? So you can use this for the analysis, okay? You don't need to simulate this. This is very trivial. Then from the circuit analysis of this, you obtain this, and you go back to the previous asymptotic plot, and you can easily predict this, okay? So implication of this, so you get this transfer function, frequency response of transfer function. So understanding the implication of this is very important. So there are many implications. Actually, frequency response of any system, any linear time invariant system, it carries all the information about the steady state and the transient period of that system, okay? Entire information about the system is contained here. So just one simple example is shown here. This is the simulation result, okay? So I simulate the input to output response, okay, based on the previous analysis. So using this method or this circuit analysis, you obtain this. This is the input to output transfer function. This is actually the frequency response, and this is the frequency of your interest. And I select one particular frequency, which is this one, 2 kilohertz. At that frequency, the magnitude of frequency is minus 20 dB, and the phase delay of that at that frequency is, this is, for example, minus 20 dB, and this is minus 130 degree, okay? So the meaning of this information is interpreted using this time domain simulation. So this is the Bode converter, and this is the time domain model, and the QT is the switch drive the signal. So this is the periodic, and this is called on-time period remain the same. Then duty ratio is fixed. This is a steady state, okay? It periodically turns on and turns off, and assume the duty ratio is this one, okay? So duty ratio is fixed at this value. Originally, the input voltage of this converter was 16 volt. It was fixed. Okay. But you add this head is sinusoidal component. So the average value is 16, but some sinusoidal component is superimposed on it. And the magnitude of this is this one, 0.5. Okay. So 0.5 is here, and this magnitude of this sinusoidal oscillation is 0.5, and the frequency of this sinusoidal oscillation is 2 kilohertz here. So this is the frequency of sinusoidal oscillation. Then the prediction of this, okay, based on the principle that, okay, then input voltage is given by this. Input voltage is the DC 16 plus some AC component, sinusoidal component. Magnitude is 0.5 and the frequency is 2 kilohertz. At 2 kilohertz, this input to output transfer function predict this minus 20 dB attenuation. That means because this is the buck converter, so this is the DC and the DC output is 16 times Dewey ratio. So this is the steady state DC, which is 4, okay? But this one is attenuated, okay? And attenuation factor is minus 20 dB, which is 0.1. So this is a 0.1 times 0.5 becomes this one, 0.05, okay? And there is this phase delay to this sinusoidal component at this frequency. So you have phase delay of 130 or minus 130 degree. So this is the output. This is DC output, and this is the sinusoidal component output. Okay, and so if you take a look at the output voltage of this, it has this switching ripple component. This comes from the switching action of switch employed in the converter. So this is something else. You should consider this separately. So there is a ripple component. Okay. This model cannot predict this ripple component, this one. Okay. So you should consider this separately. But there is if you connect this envelope of this out voltage has some sinusoidal variation, low frequency variation at the same frequency with this one, and the magnitude is reduced by tenths. Okay, so this magnitude is 0.05. Okay, so sinusoidal amplitude inserted into input voltage is 0.5, but sinusoidal component at the output is 1/10 of that, which is correct. Okay, if you take a look at the phase start at 0 degree, but phase here is something else. Okay, so difference between this and this is the phase delay. So our voltage is this one, and some ripple component. You should consider this separately, but this is very easy to calculate. Okay, from the steady state analysis of a converter, this can be easily figured out. So this is the result. Okay, this is the one implication of this plot. There are many information about this converter in this frequency response plot of input to output transfer function. Okay, so this is just one simple example. Maybe you take another point here. That means the frequency of this sinusoidal variation has been changed. Then attenuation will be increased, and the phase will be reduced. Phase delay will be reduced. So all the information is here, right? Another example. Okay. This is the PSIM simulation. Another example. Let's consider Dewey ratio to output transfer function, which is this one. Okay. For that, this was the previously that the 0.95 was fixed at this point, and the input voltage contains some sinusoidal component. Now this is fixed. Okay. It has only DC, but this some sinusoidal component is added to this one, that means we are perturbing, we are changing this control signal, and we perform this PWM, then output will have the sinusoidal component in the similar manner to the previous case. Okay? So previously, the sinusoidal component was added here. Now you are adding sinusoidal component here. Then duty ratio will be changed in sinusoidal fashion. Okay? So for that case, we simulate from here to there. This is the input and this is the output. Okay? But we want to know the duty ratio to output transfer function. But this is control to output transfer function. So the ratio between this one is VOSW divided by VD. Okay? So from here to there has one gain. That gain is defined as FM modulator gain, and gain from here to there. So we are changing duty ratio D. So that is GVD. Okay? So what you are measuring here is not this one, but this one. This one times this one. FM is embedded at this voltage, and FM is called modulator gain. So FM is 1 divided by this lamp signal. So this height of lamp, which is 3.8. Okay. So what you are seeing here, what you are seeing in the output of this is 20 log VOSW is sum of this times this. So in log scale, this multiplication becomes addition. So actually what you are measuring is this one. So this plus this, and you want to have this one, okay? You want to measure this one, then you have this calculation, and this becomes 12 dB. We have minus sign here, so this one is smaller than unity. So this value is negative, negative times negative positive. So what actually you are seeing is this one. So from this, you should extract this one, okay? So this Vs is this plus this, so you should print out this, okay? You understand this, all right? There is just some scaling factor because of this, all right? And this is the simulation result. Computational method using time domain model. So same result. So this we have this double pulse frequency, ESR0, some high frequency noise, and this value is 20 log Vs. This is low frequency value, 20 log Vs. Okay, so this is the time domain approach, and the smart people, they know the small signal model of this. Okay, and from this small signal model, this transfer function is directly evaluated. Consider this. So now we are measuring the transfer function from duty ratio to output, and this one is 0. So there is a current source. Okay, that current will be circulating this because this is shorted. So only this current is circulating this. Okay, and then this voltage, this is shorted. Then this voltage appears here. Then this coefficient is multiplied with D. Then you have Vs, and the remaining part is the voltage division, same as the previous case. Okay, so Vs is coming here, so everything remains the same. Okay, so I'm talking about the implication of the small signal model and validation of that using this frequency domain small signal simulation using PSIM and large signal switching model time domain simulation of the PSIM, and we have this frequency response plot, which is the same. Okay, there are 3 ways of doing this. One is this from this equation, and another one is using this method. Another one is doing this simulation. All of them should be the same, except this high frequency noise coming from this time domain simulation. Okay, cycle by cycle simulation. And the implication of Dewey ratio to output transfer function is very similar to the previous case. Here, this is a fixed, okay, but Dewey ratio is changing, right? Maybe Dewey ratio is changing cycle by cycle. Maybe this part is changing. This part is changing. And this part, the other part remain the same. This length of this can be considered as steady state Dewey ratio D, which is 0.25 here, and this bearing part is D hat. Okay, so in terms of graphics, maybe this D represent steady state Dewey ratio, and this one, this shaded one, is the bearing part of this on time, is represented by D hat. Small signal change in Dewey ratio. Okay, so you plot this using any of three methods I explained, and you obtain this, and you take a look at one particular frequency, which is 5 kilohertz. At this 5 kilohertz, this is 5 kilohertz. This phase is minus 135 degree. Assume this, and this magnitude is 0 dB. 0 dB means what? 0 dB is unity, so magnitude remain the same. Okay, that is the meaning of this. At this frequency, magnitude will be increased more than 10 times, and it remain the same, will be decreased at higher frequency, something like that. All right. And here, this is the fixed, and Dewey ratio is here. But if you take close look at this, the on-time period will be changing. Okay, you cannot see this here, but the on-time period is large here and small here, large here, small here. Okay, and the variation of this is sinusoidal, something like this. Okay, so this Dewey ratio is increasing and decreasing. Okay, but in time domain it is increasing and decreasing in sinusoidal fashion. Okay, so I generated this using some simple circuit. So I was able to generate this switch drive signal whose Dewey ratio is changing in sinusoidal fashion with average value of 0.25. Understand this? Okay, and the magnitude of this is DC is 0.25, and the magnitude of this variation is this one. So variation here is 0.05. Okay, then Dewey ratio is this one. This is the D, and this is the D hat. Okay, D hat is sinusoidal component. Input voltage is 16. Then DC value of our voltage is this times 16, which is 4. Right? So 4 is coming out as a DC, and this sinusoidal component in Dewey ratio is multiplied by 1. 1 is here. So it remains the same. So our voltage is this. And at this frequency, there is a phase delay of 135 degree and some ripple component. So ripple component is here. And this is a ripple component here. Okay? You see this. If you take the average value of this, ignoring the ripple component, this is also, this variation is also 0.05. Okay? So it validates the implication of this transfer function, Dewey ratio to output transfer function. It's just one point. Okay? If another point, you may have different result. And again, this frequency response contains the entire information about this system. Okay? Okay, I have one page, summary page. This is a summary of the lecture 1. Okay. What you have done, what you have learned in lecture 1 is basically this one. This is the Bode converter. This is Bode converter. Okay. This is A terminal, P terminal, C terminal here, and this RL is ignored because very small. RC is small, but this cannot be ignored because it creates the ESR, omega ESR, ESR 0, which is very critical in determining the magnitude and the phase of this transfer function. If you ignore this, you don't have this, then everything will be changed. Okay? If you have RL, it only changes the DC value slightly. It only changes this part very slightly. So this can be ignored, or you cannot ignore this. Okay? So ESR is always important. You should take into consideration in analyzing something or simulating something. Okay? Again, this is the switch drive signal. So some of this is the D plus D hat. This is better. This part is D. This bearing part is what? This is a D hat. Okay? So this is bearings. In sinusoidal fashion, maybe this is 0, variation 0, and increase gradually and get the maximum value and decrease gradually like this in sinusoidal fashion. That is the definition of perturbation in Dewey ratio. Okay? So from this, you have a small signal model of this. Then you obtain this. So this transfer function, input to output transfer function, and Dewey ratio to output transfer function. Okay, very simply, right? And this W per frequency is given by this, and the Q factor, quality factor is given by this. I explained why it has this form. It should have this form. Okay, and this ESR 0 is given by this. That 0 is coming from here. So you have one branch. At this frequency, this impedance becomes 0. Then output is 0 because the output port is shorted. So whatever you have here, output is 0. That is the definition of 0. Okay. So for this case, you have this type of frequency response. Probably this one. This one. This is the magnitude of input to output transfer function. Okay. And this is the W per frequency is somewhere here. And this is the omega ESR. ESR 0 created by equivalent series resistance ESR of capacitor. That's called the ESR 0. I said the whole information about this circuit is carried by here. Okay. Let me give you 3 examples. First, input voltage is changing like this. This is the DC value, and there is some low frequency sinusoidal component. Then sinusoidal component will be reduced a little bit. Okay, maybe somewhere here. Then will be reduced. Okay, so DC in, DC out, and AC in, AC out. The magnitude of AC is somewhat reduced. Okay, if the frequency is somewhere here, they remain the same. The same magnitude as the input will appear here. Okay? Now you increase the frequency of the sinusoidal variation here, somewhere here. Then you have larger attenuation that at high frequency, attenuation is increased. So this is much reduced. Okay? So you have very small ripple component at higher frequency. Okay? So this information is obtained continuously for all frequencies. Okay. Suppose you applied some arbitrary waveforms, some this triangular type waveforms, periodic waveforms. Then that periodic waveform can be decomposed into sinusoid component with many frequencies, fundamental frequencies, higher order harmonics. Okay. Then you use superposition. Consider one component and another component and something like that, and add them all together then you have complete knowledge about the output due to that periodic signal, which is a non-sinusoidal waveform. Okay? Because of that, you have the entire information about this in steady state transient response. Okay? Suppose this case, the input voltage is changing from Vs, it steps up to Vs prime and steps down the original value of the Vs. Then our voltage here will be D times Vs, here D times Vs, but during this time period, there is some transient response, and this response will be D times Vs prime. So Vs prime is larger than Vs, so it will go up, and it will show some transitional behavior, overshoot, undershoot. Okay. Then the behavior of this waveform during transient period can be precisely expected from this information. Okay? That is what I mean. All the information is contained this frequency response. So knowing the transfer function and its frequency response is the same as knowing every information about this system. Okay? So this one is important. Bode plot is important. Frequency response is important. And relating the frequency response and other performance is important. Okay? You will be learning all these techniques in this course, and you will use that information to design the feedback controller and analyze the complicated behavior of converter. Okay? I took one example using GVS, and I can prepare another example using GVD, but this one is not easy. This one is extremely easy to see. Everything is simple and apparent, so you can easily accept this. But this one is tricky to show something like this. But I'd like to emphasize this. This GVD contains all the information required to design the feedback controller for the stability and good closed performance. So this is the most important transfer function in this converter, okay? Because eventually we will be changing duty ratio of this converter, any converter, to achieve any design goal or to improve the performance of the converter. All you can do is change this duty ratio. So knowing this transfer function, this characteristic of this transfer function is it provides a vital information on the control design and the closed loop analysis. Okay?